Okay guys, so today we're going to talk about escape velocity. Alright, so what I have here to represent escape velocity is a wooden ramp. Now watch as I roll this ball up this ramp. It's going to come right back down. So escape velocity is essentially the velocity needed so that you can roll this ball and it'll go all the way past the ramp and be fine, and not be affected by the ramp anymore, or be affected by gravity anymore. So our escape velocity is the velocity we need to get the ball over the ramp. And now watch. The ball keeps on coming back down, but if I give it enough velocity, the ball goes over the ramp. And now look, I want you guys to see this. This will make a lot more sense when I show you the equation. If the ball goes past the ramp, let me change that. All right. So if the ball goes past the ramp, now watch. The ball doesn't have to move anymore. The ball doesn't have to try to escape anything. The ball actually has zero potential and zero kinetic energy, right? In reference to this ramp. And this ramp represents our gravity. So we're looking for the velocity needed so that this ball can make it all the way past this ramp to where it doesn't get affected by the ramp anymore. Let's go derive the formula for that. Now, what we see here is a picture of our beautiful blue Earth, all right? And that line represents the radius of the Earth. Okay, the radius from the surface to the center of gravity. Now, our escape velocity formula, we're going to derive from the conservation of energy. Okay? Now follow along. We have some sort of kinetic energy that we use to fire off. That's our initial kinetic energy. Remember, we need velocity. So velocity is within our kinetic energy formula. Plus the potential energy. Our potential energy is how much we want to come back down. All right? So as soon as we fire off, our potential energy is getting greater and greater and greater and greater. All right? Is equal to our final kinetic energy plus our final potential energy. So 1, 1, 2, 2. Now, remember what I said about not being affected by the ramp or by gravity anymore. Our ball is stationary. It's not being pulled down by the ramp. It's not being pulled down by gravity. So our potential energy at a point infinitely far away, all right, our potential energy is equal to 0. And our kinetic energy at that point is also equal to 0. It's equal to 0 because our ball isn't moving anymore. It's stationary. It's 0. So again, we're not being affected by the gravity anymore. We're not being pulled down anymore. So our potential energy is 0. And we're not being affected by the kinetic energy. We don't need the velocity anymore. We don't need any more velocity. We're good. We can stop. So our kinetic energy is 0. So what we're left with is kinetic energy, which I'll write out, 1/2 mv squared, plus our potential energy, and we'll just keep it like this for a second, mgh is equal to 0. Equal to 0. So I'm going to pause it right here. So now here's what we need to realize. We need to realize that we have two different directions, all right? Our kinetic energy is going away from the planet, but our potential energy is pointing towards the planet. So our potential energy, if we really want to make this right, is 1/2 mv squared minus mgh equals 0. So the kinetic energy minus potential energy is going to give us 0. Now, we need to put something else in here for g. Remember what we derived out earlier. We said g was equal to capital G, capital M over r squared. G is equal to the gravitational constant multiplied by the mass of the Earth divided by the radius of the Earth squared. So if we plug that in right here, we'll get 1/2 mv squared minus m g m over r squared times h equals 0. Now, remember, really what r squared is our distance. R squared is our distance from the center of gravity. So when we're on the surface of the Earth, r squared is just the radius of the Earth. But r squared really means the distance from the center of gravity. Our h also represents that exact same thing. Our h is the distance from the center of gravity. So really what we could do is we can cancel out these two h's right there. So we'll cancel out h, and we'll take that away from the r. So it's just left with r in the bottom. And now, let's rearrange our equation. So we'll say, okay, 1/2 mv squared is equal to g, capital M, I'll put lowercase m for the mass of our object, divided by r, or the distance we are from the center of gravity. Now, we actually have the mass on either side of the equation, so we can cancel that out too. This is the mass of our object, or whatever we're sending out there. So mass doesn't matter with this. So now we have this. We have 1/2 v squared, and I'm going to start putting VE here because that's now becoming our escape velocity, is equal to gm over r. We'll multiply by 2 to get rid of the 1/2. And we're left with, as we see over here, v squared e, or our escape velocity squared, is equal to 2gm over r. And to find our escape velocity, all we have to do is just take the square root. Take the square root. So our escape velocity is equal to the square root of 2gm over r. That's what you need to know.